Oh, good morning. Somehow I'm not able to see your chat. Someone can unmute whether am I audible. Am I audible? One of you can unmute and answer.
Yes, sir.
Okay, fine. We'll start. So we'll start a new chapter on Turing machines, which is considered to be most general model of computation and developed by Alan Turing in the year 1936. Much before the first general purpose computer was developed in the year 1944. So actually the idea of the general purpose computer emerged from the Turing machine. Now look at these languages L1 and L2. A raised to n, B raised to n, C raised to n, ABC belongs to sigma, and L2 is SS, where S belongs to AB star. Now the first language can be accepted by two-stack model. In the case of PDA, it is having a single stack. So a PDA cannot accept a language such as L1 because it needs two stacks. It has to match number of A's with B's and C's. So if it has to match something like only A's with B's, that is fine. But here in this example, it has to count number of A's and then compare with number of B's and C's both. So if there are two stacks associated with a PDA, then it can accept a language such as L1. However, a PDA has only one stack. Therefore, L1 cannot be accepted by a PDA and it is not a context-free language. Similarly, L2, SS means the first half symbols, it is same as the second half symbols. For example, ABB, ABB. First half is ABB, the second half is ABB, and here first half is same as second half. All such strings will be there in L2, and it cannot be once again accepted by either finite automata or using PDA, because here the data structure needed would be queue instead of stack. If the model has queue as the data structure, then it can accept the second language. Once again, we cannot change the data structure of these models, whether it is finite automata or PDA. So examples of languages which are not accepted by a PDA, they are L1 and L2 and many such similar languages. And once they are not accepted by PDA, no question of getting them accepted by finite automata. So to solve these problems, problem of accepting such languages, a generalization of existing model was required. Generalization of existing model was required. And normally we'll think of enhancement of PDA. And that is what we thought, in the case of L1. If you have two stacks, then we can accept it. So normally we would think about enhancement of a PDA. However, Turing did not think about that. He thought of what is called human computers. Turing he gave idea of what is called human computers. That is, a person sitting with a paper and pencil and solving a problem in an algorithmic way. A human being sitting with a paper and pencil and solving a problem in an algorithmic way. And the action of a human being comprises of examining the current symbol, erasing it, and looking at the other part of the paper. What does a human being do? He looks at the current symbol, he erases it, and looks at the other part of the paper. And the corresponding actions, machine actions, are actually changing the current symbol, moving the head to the left or right, changing the state. So a Turing machine, there is a tape which is considered to be infinite size. The length of a tape in a Turing machine is infinite. And the actions associated with the machine are changing the current symbol, moving head to the left or right, and changing the state. So in the case of a Turing machine, the tape, which is linear in nature, it is the input, memory and output device, because whatever the content, the initial input, that is stored on the tape, the computations are being made on the tape and stored there. So it's a memory device as well, and the final output, that is also stored on the tape. So it is the input, memory and output device. Basically, the Turing machine, it comprises of a tape which is considered to be infinite in length. We'll discuss this more later on. Now, a statement that was provided by Church, an American logician, regarding the power of Turing machine, that is called Church-Turing statement or Church-Turing thesis. And this is a very powerful statement. Anything that can be expressed as an algorithm can be executed on a Turing machine. A very, very powerful statement, because what does a computer do? In order to solve any problem, it requires an algorithm, its implementation. Ultimately, the program, set of instructions. What can a Turing machine do? Anything that can be expressed as an algorithm can be executed on a Turing machine. So a Turing machine is as good as a general purpose computer. Turing machine can also compute functions. So far, whatever models that we have discussed, may that be finite automata or PDA, they are basically for language acceptance, or there's something called language recognition. The difference between this you may study after this chapter. As of now, the acceptance and recognition terms we interchangeably use. So all these machines, all these models, they were for language acceptance, whereas Turing machine can also compute functions. It's not only for language acceptance. So that is how a Turing machine is more powerful than other models of computation. And its power, this is a very big statement as such, which express power of a Turing machine. You give an algorithm, anything that can be expressed as an algorithm can be executed on a Turing machine. And even our general purpose computer without an algorithm or a program or a set of instructions cannot function. So what is, for whichever problem there is an algorithmic solution, can be executed on a Turing machine. That is the power of a Turing machine. With that introduction, now we go to the next part, that is formal definition of a Turing machine. A Turing machine TM is a 5-tuple Q sigma tau Q0 delta. Most of these symbols you know. Finite set of states is Q. Finite set of input alphabet is sigma. This is different, tau. That is a finite set of tape alphabets and does not include the symbol blank. Turing machine basically, that is infinite linear tape. And the tape alphabet, that is the set of finite set of tape alphabet, that is called tau. The initial state is Q0, same symbol, Q0 belongs to Q, Q is our set of states. The state transition function is delta, and the type of function delta is Q cross tau union blank to Q HAHR tau union blank LRS. Transition function. So mu is decided by the current state, that is Q. The current symbol on the tape, the current symbol over which the read-write head is placed. There is a tape and there is a read-write head with a controller. That is the basic architecture of a Turing machine. Tape, the linear tape, and there is a read-write head, and there is a read-write head's controller. So state transition function is a state, that is Q, tau union blank, that is the tape alphabet, and the action part, that is right hand side of the arrow, making a transition to the new state. If you look at the human computer, then action of a human comprises of examining the current symbol, that is the present symbol, is person's frame of mind, that is current state, new symbol, erasing it, and looking at the other part of the paper, so moving to the next symbol or the tape. So here our transition function is the current state, that is Q, current symbol or the tape, that is tau union blank, new state, that is Q union, there is something called HAHR, the halting state and the rejection state. HA and HR, these are not part of the set of states. These are special states. HR is not compulsory, that is halting with rejection. HA is halting with acceptance. Mandatory is HA. We will discuss more about this HAHR. So making a transition to the new state Q, and because HAHR, these two states are not part of Q, so it is Q union HAHR, that is new state. Writing a new symbol, so that is tau union blank. So symbol from tape alphabet, and because blank is not part of the tape alphabet, it is union blank. So present state, present symbol, new state including HAHR, new symbol including blank, and looking at some part of different part of the paper, that is my displacement. So that is left displacement, right displacement, and no movement, that is stationary, LRS. So action comprises of new state, new symbol, and looking at different part of the paper, that is our displacement, LRS. That is how we have mapped action of a human computer. Once again, the action of a human computer comprises of examining the current symbol. So it's his current frame of mind, looking at the current symbol, so that is Q, and the symbol, and erasing it, that is a new symbol, and looking at some part of the paper, that is my displacement. We are moving the head to the next part on the tape, that is called actually cell, next cell on the tape. Fine. So this is my state transition function, and the tape is considered to be semi-infinite in length. I'm not getting, I'm not taking your feedback. I'll communicate in a one way only. I'm not reading your messages. Any question you have, we can discuss in the next lecture. Fine. So, we continue. Tape is semi-infinite in length. If someone has a doubt, can unmute and ask me, no issue. Can stop me, unmute and ask me. Tape is semi-infinite length. Semi-infinite computationally actually is infinite. It is considered to be semi-infinite in length because it has a left end but does not have a right end. It is infinite towards the right. Therefore, instead of infinite, sometimes you will find the word semi-infinite also. Tape is considered to be semi-infinite in length because its left end is fixed and it is infinite towards the right. That is the meaning for semi-infinite word. Computationally, in terms of number of cells, it is infinite. The tape is divided into squares. The tape is marked off into squares, and these squares, they are numbered as 0, 1, 2, etc. from left. It is a fixed left end. It is divided into cells. Those squares or the cells, and these cells are numbered as 0, 1, 2 for our reference only. These numbers, a TM does not recognize these numbers. This is for our reference only. A TM doesn't recognize cells by these numbers. For our reference, we'll say the leftmost cell, or the leftmost square, that is 0, then 1, 2, etc. Otherwise, TM does not operate using these numbers. A TM has a head which moves to the left, right, or remains stationary. So that was our displacement actually in the formal definition. The second part, the displacement part, this one, LRS, that is head either remains stationary, that is S, moves to the next square or next cell, that is R, goes to the cell which is left of the current cell, that is L, the displacement L. Movement of the tape is cell by cell, one cell at a time. Either it remains stationary, moves to the left, or goes to the right. So that is my displacement. Head moves to the left or right, that is LRS. Fine. Now, movement is cell by cell. Now, move of a typical move of a Turing machine. So my present state is Q. The next state of the TM is R. And a move state transition function, we know its type already we have seen. A move is decided by the present state and the present symbol below the read write head. So if you look once again, go back to that, the definition. state transition function. It is q cross tau union blank. So present state and then present symbol, then new state, new symbol, and the displacement. That is how it looks. Q, that is my current state. My new state is R. So delta QA, current state is Q. Current symbol below the read write head is A. Next state is R. Now this A symbol, the current head is over a square, its content is A, that is changed to B. So that A becomes B. The notation is A/B. A is replaced with B. My present state is Q. My current symbol is A. My next state is R. The new symbol is B. And the head moves to the next cell towards right. That is the displacement R. So current state move is decided by the current symbol in the current state combination. That is delta QA. The action part is new state, that is R. New symbol, that is B. R the displacement. So that is our notation. Q, R, and over that arrow we'll write A/B R. So A is replaced with B. Present state Q, present symbol A, new state R, new symbol B, the displacement R. So either that notation or delta QA equal to RBR. So both the things are same. That is move of a Turing machine. And there's something called configuration of a TM, which indicates the current state of a TM. And it is a pair QXAY. The current status of a TM, that is a pair. What is the status of a TM at any point of time? That is a pair. What is that? QXAY. Q means the current state. A, that is the current symbol. And because blank is not part of the tape alphabet, we say tau union blank. The present symbol, that is the symbol over which the read write head is placed, maybe any of the tape alphabet, maybe blank also. So that is tau union blank. A belongs to tau union blank, and XY, these are strings over tau union blank, which means it is tau union blank star. Any combination of the tape alphabet symbols and blank, that is meaning of tau union blank whole star. Tape alphabet plus blank and any combination of that, that is star. That is any combination of that, there we apply the star operator. So XY belong to tau union blank star. Basically what it is, the present state, that is Q, and XAY, that is my tape content. Whatever symbols that we have written over the tape, those symbols are XAY. A means on a particular symbol or a particular symbol, the read write head will be placed. So it is underscore below A. That is my current symbol. To this current square, towards left, I have some symbols. Those are indicated by X. Towards right, I have other symbols. Those are indicated by Y. So basically it's the tape content. XAY together is nothing but the tape content. Except for this content of XA and Y, because the tape is infinite in length, the remaining squares will be considered to be blank. Nothing is written. So what is important? What is the current state of the Turing machine? And so far, what is the content of the tape? What we have written on the tape? So that is XAY. And at particular time, we'll place the head over a particular symbol, that is over the symbol A. That is the meaning of underscore. To the left of A, I'll have certain symbols represented by X. I have other symbols represented by Y. I have to indicate where exactly the read write head is placed because it moves cell by cell. So that is the term current status of a TM. What is its current state and what is the content of the tape at that moment? That is the status of a TM. And TM moves from one configuration. That is the meaning of configuration. The current state and the current content. TM moves from one configuration to another configuration, and that is represented symbolically as QXAY. There's the current state Q and the tape content XAY. Then moves to the next configuration, that is the state R, and this is ZBW. That's the new content of the tape. And we are talking about a Turing machine T. Therefore, we have written T below. So one configuration, next configuration. That is a single move. And over the multiple moves, it goes to the new configuration. So star we are writing QXAY to R ZBW star. It means moving from one configuration to another configuration in 0 or more number of moves. So that is how we apply the star operator. Present configuration, next configuration. Fine. A condition for acceptance of a string is here. And here comes the halting state into the picture. Accepting a string by a Turing machine T. So it starts with a configuration Q0 blank X. And ultimately it has to reach the halting state. The condition for acceptance of a string by a TM is initial state is Q0. As per the formal definition of a TM, the initial state is Q0. We are checking whether the string X belongs to sigma star is accepted by a Turing machine T or not. So initial configuration means initial state, that is Q0, and blank X. What is the meaning? See, underscore, that is over the blank. It is below blank. What does that mean? The initial position of the read write head, that is over blank. And then we have our input string X. There is a fixed left end in the case of tape. So cell number 0, that is kept blank. And initially head is positioned over cell number 0. And my X string starts from cell number 1. Suppose my X equal to A double B. Then the content of cell number 1 will be A. Cell number 2 will be B. Cell number 3 will be B. Cell number 0's content will be blank. So this is my initial configuration Q0 blank X. And then the requirement for acceptance is ultimately it has to reach the halting state. So this is a special state. If TM goes to the HA, then the string gets accepted no matter what the tape content is. So YAZ could be anything. String Y can be anything. Symbol A, anything. String Z, anything. Whatever the content may be, if it goes to the halting state, string gets accepted. So symbolically Q0 belongs to capital Q, that is a state. X is our input string. We are checking acceptance of X. Therefore, X belongs to sigma star. HA is our halting state. YZ are strings, any string. A, the head is placed over the symbol A. To its left, there is a string Y. To its right, there is string Z. So YZ belongs to tau union blank star, any string. Symbol A could be any symbol of tape alphabet, including blank. So A belongs to tau union blank. So whatever Y may be, whatever A may be, whatever Z may be, doesn't matter. Matters is the reaching halting state. If TM reaches the halting state, string gets accepted, no matter what the tape content is. Now this function is different of a Turing machine compared to other models of computation, where the entire input has to be processed. Whereas here, if TM goes to the halting state, the string gets accepted. We'll discuss more about this later. That's fine. So this is moving from initial configuration to the halting state for accepting a string. In general, LT, language accepted by Turing machine T, that is LT. It contains all strings belonging to sigma star. Any string that belongs to sigma star with the condition X is accepted by T. Any string X that is accepted by T, all such strings, they are part of the language L accepted by Turing machine T. And what is the meaning of X is accepted by T? The above definition, accepting a string by a Turing machine T. Q0 blank X, HA, YAZ. So all those strings that are accepted by Turing machine with those conditions reaching to the halting state, the condition is going to the halting state. All such strings are part of language LT. So LT is language accepted by Turing machine T. In general, a TM may, we are looking at the definitions and the terms before we take the first example. Don't worry, we'll start with the example. All these terms will be clear. In general, TM may halt, it may crash, it neither halts or nor crash. These are possible actions of a Turing machine T. A TM may crash, neither halt nor crash, or it halts. What is that? Crash. Examples of condition under which a TM is said to crash. Number 1, delta QA equal to phi. So my present state Q, my current symbol A, and for that state symbol combination, I don't have any move. Delta QA equal to phi. It means in that case, a TM is said to crash. Maybe invalid operation. For example, moving head to the left of the cell 0. See, there is a leftmost end in the case of a tape. and our operation, the displacement, suppose specifies L move, left move, then it is moving to the left of the zeroth cell and no such cell is there. So that is invalid operation, moving head to the left of the cell 0. So these are the conditions for crash, and for these condition a TM is said to, I mean the conclusion of a TM is rejection of the string. The TM is said to crash, implication string is rejected. So a TM may crash under conditions like delta Q equal to phi, invalid operation. A TM, last part, a TM halt, halting state is reached. As we said in the acceptance of a string condition, if we reach halting state, no matter what the tape content is, string gets accepted. So here, third part, halt. Halting state is reached, string gets accepted, that's it. Once we reach halting state, we don't need to process further input. String gets accepted. And the third possibility, the middle one, we say TM neither halts nor crashes. That is indefinite looping. It is not halting, it's not reaching to the halting state, it is not crashing. So it neither halts nor crashes. In that case, the string is neither accepted nor rejected. That is the case of indefinite looping. We have not taken the care. TM may go into an indefinite looping. It will go computing forever. String is neither accepted nor rejected. That is indefinite looping. So these are the three possible cases in the case of a Turing machine. The three possible actions of a Turing machine. Turing machine may crash, may halt, neither halt nor crash. These are three possibilities. So with these examples, with these definitions, we quickly move to the first example. Look at this. X belongs to AB star. X contains the substring ABA. This is my first example. We construct a Turing machine T. We construct a Turing machine for accepting this language. X contains the substring ABA. We know the given language is a regular language. The first example, language L, it is a regular language. It must contain ABA. My RE is what? A plus B star. ABA, A plus B star. Bracket, A plus B star. ABA, bracket, A plus B star. It must contain ABA string, no matter what the prefix is, what the suffix is. So any such string belongs to L. And because we can write an RE, regular expression is A plus B star, ABA, A plus B star. So because we can write regular expression, the language is regular. And because the language is regular, we also have a finite automata. Language is regular, we always have a regular expression, we always have a finite automata that accept the given language. That's the condition for regularity. Regular language, there is a regular expression, there is also finite automata. And very simple to construct DFA for the given language. Again, this is not part of constructing TM. Just for understanding the language L, we are starting with constructing an FA. And constructing FA is also simple. We are looking for the pattern ABA. So whenever we look for a specific pattern, a rule of thumb for number of states in the FA could be the length of the string plus 1. Whenever we are constructing FA containing strings having a particular pattern, a rule of thumb for constructing FA, in particular DFA, it is number of states would be length of the string plus 1. For example, here we are searching for ABA. So Q1 we have written here, doesn't matter. Q1, Q2, Q3, Q4, you put ABA. So ABA, there is initial state as well as the ending state, the accepting state, that is Q4. Initial state here is Q1. So total states 4, length of the string 3. So whenever we construct FA for a regular language such as this, where strings contains a particular pattern, then we can have that length of that pattern plus 1 number of states. So here 4, ABA 3, number of states 4, and we write ABA to begin with, and then we add remaining transitions. In the initial transitions, we have put Q1 to Q2A, Q2 to Q3B, Q3 to Q4A, that is ABA. So if we get ABA, we reach the accepting state. Now let us look at Q4. Once we have the string ABA, we don't care which are the other symbols. The second part, A plus B star, ABA, then A plus B star. That is my regular expression. So once the pattern ABA is found, we don't worry about, we don't need to check anything about the remaining symbols. But then we need to process them. We have to go till the last symbol. Therefore, in the state Q4, we write A comma B. Remaining input, we don't need any matching, just ignore them. A plus B star, ABA, A plus B star. That is my regular expression. So after ABA detection, the last part of R is A plus B whole star. So just ignore them. Therefore, in the state Q4, we are skipping the input symbol. Still we remain in the accepting state because the pattern ABA is already detected. String is acceptable. Only we need to complete formality for reading the remaining input. And result is already declared. String gets accepted. So we never come out from that accepting state. We cannot come out from that accepting state Q4. So in the state Q4, it is A comma B. Fine. Now let us look at the initial part. Suppose my input is starting with B. So those I'm searching for the pattern ABA. And if my input string starts from B, then it is not part of the pattern ABA. So I skip those initial B's in the state Q1. Unless I get the first A, all initial B's, they are not important to me. I'm matching the pattern ABA. So I skip those B's in the state Q1. On getting first A, I make a transition to Q2, Q1 to Q2 on A. And once I get the first A, then suppose I have many such A's, again, those A's are not important to me because I'm looking for A, B, A. So for example, my pattern is a triple A, B, A, and then something. So once I read the first A, remaining two A's not helping me much. So I skip that in state Q2. Out of three A's, only the last A is important because I am looking for the total pattern, consecutive symbols A, B, A. So in the state Q2, I skip remaining A's. I have found one A, I'm looking for the next B, and on getting that B, I go to the state Q3. Now I have so far found AB. Q2, I go to state Q3 on B. AB is found. Now after AB, suppose some A's are there, and then I get B. So last two symbols are AB, and instead of getting A, suppose I get B, A, B, B. Once again, as I'm searching for the pattern ABA, successive symbols ABA, getting B in the state Q3, not important to me. So I make a transition. Again have to do pattern matching for the entire substring ABA. So in the state Q3, on getting B, I'm back to state Q1. Whatever AB, the part of the string AB that was found so far, after AB, if I get B, then it's not going to be useful to me as it has to be ABA. And if we get ABB, again, I have to search the total string once more. Therefore, back to the state Q1. So these are the remaining transitions. This is my finite automata. Finite automata that accepts the given language. The given language is a regular because we have a regular expression corresponding to that. Alternatively, we can also have the finite automata that accept the given language. Therefore, the given language is regular. Fine. The question is, language is given to us. We can construct FA as it is a regular language. Now, our Turing machine. Once again, please understand that there is no need to construct FA. Just to understand the structure of the language, and as we are comfortable with constructing FA, we started by constructing FA for the given language. Otherwise, we have to straight away construct the TM. And this is my corresponding TM. Initial state is Q0. Now Q1 to, instead of Q4 accepting state, here HA. And once we reach the halting state, we don't need to process the remaining input. Look at Q4. That is finite automata. I need to complete reading my input. Whereas in the case of TM, once we reach the halting state, the string gets accepted. We don't worry about the remaining input symbols. We don't need to process them. So you see no transition defined from the state HA. Initial state Q0 is added, otherwise structure wise, basically it is Q1, Q2, Q3, and now instead of accepting state Q4, we have renamed that as HA. Logic remains the same. Looking for the pattern ABA, here is the Turing machine notation. Now, if you look at this state Q1, the transition is BBR in the bottom second figure, that's a TM. Logic is same, I have to skip B. But as per the notation of TM, what is that? We replace B with B and the displacement is R. My input is there, my input string, whatever it may be, it is stored on the tape. So if my current symbol is B, in fact, I don't change, I don't require processing, I am just comparing. So in all these moves, you will see BBR or AR, nothing else, because I'm not changing the tape's content. It's in the reading mode only. There's no writing required. I'm inspecting whether the string ABA is present in the input or not. So I read a symbol, don't change it. There's no need to change that. I don't need to process that. Just read it and just save it. Remember that what symbol I have read. So logic remains the same. So you'll find B/BR. Again, Q1 to Q2, it is AR. Q2, again AR. So I'm searching for A. Once I find A, I replace A with A and go to the R. My displacement is R so that I can read the next input. Input is stored on the tape. So I'll read a symbol. I'll check whether it is useful to me and then make appropriate decision. So in the state Q1, same on B, I have to skip initial B's. So it is BBR. I stay in the state Q1. So go on skipping all B's. Once I find A, I go to state Q2 and I don't change A. So A is replaced with A. I'm not changing the content of that cell and going to the next cell for checking whether B is there or not. So it is AAR. In the state Q2, again, I'm just skipping all A's. So the move is AAR. And then on getting B, we are going to the Q3 state. Again, Q3 to Q1, finding B, it is BBR. Again, if I get B in the state Q3, then I go back to state Q1 as I have to once again start searching for the pattern ABA. So this is my TM. Only the Turing machine notations we have used, logic is same of FA. Logic does not change. The logic does not change. I'm searching for the pattern ABA and the meaning of me, take any move. Once again, I'll take state Q1. Let's say Q1 to Q2 AAR. So my present state is Q1. My current symbol is A. I'm making a transition to state Q2. My new symbol is A. R is the displacement. It is something like delta Q1, comma A. So move is decided my current state and current symbol. My current state is Q1. My current symbol is A. I'm making a transition to Q2. So next is Q2. My new symbol is A. I'm not changing the content of A. I'm in the reading mode. I just compare. I'm not doing processing. So it is Q2, comma A, comma R. That is what we studied. Delta QA equal to RBD. Current symbol Q, current state Q, current symbol A, next state R, new symbol B, R is the displacement. So here similarly here, let us take a Q1 to Q2. There are two moves. One is BBR and the second move is AR. So right now we are discussing AR. So delta Q1, comma A equal to next move Q2, comma A, comma R. Displacement is R. A is replaced with A. Displacement R means I'm moving to the next cell. So that is a TM for accepting the given language. X belongs to AB star. X contains substring ABA. I have constructed TM. There is no need to construct FA because this is our first example. Just to understand the logic, just to compare the structure, we started with constructing FA and then constructed TM. For the next example also we'll do this. From the third example onwards, we'll straight away construct the TM. So with that, we have seen the first example of a TM. If anyone has a doubt, can ask me. Otherwise, we conclude today's lecture. Is that fine? If someone has a doubt, can ask me. Please understand that in the HA state, That is our accepting state. We don't need to process further input. String gets accepted. That was the condition for acceptance of a string. See, look at this. Accepting a string, you go to the HA state, the content of Y or A or Z can be anything. Once we reach the accepting state, string gets accepted, no need to process input further. So this is functional difference between TM and other model of computation. This is one of the functional differences between the Turing machine and other models of computation. It was our this TMA halt. Three possibilities. The rightmost was halt, reaching the halting state. We'll call it HA. Reaching the halting state, we'll call it HA, halting and accepting. And there you can see in the this one. HA is not part of Q, so it is making a transition to the new state Q union HA. Also we'll use HR at sometimes. So HA HR, new symbol tau union blank, the displacement LRS. Fine. So with that we complete today's session. We'll continue tomorrow.